Okay, so now suppose we do have a Boolean function that described by its truth table. How do we go about making a circuit, or at least, since we're not getting into circuits just yet, a formula that would evaluate to true exactly when that Boolean function outputs 1 and evaluate to false when the Boolean function is supposed to output 0. For that, we will look at how to not only construct formulas from truth tables, but we will actually get formulas of easy special form, which are easier to deal with than general form. In fact, even though we will be getting formulas of easy special form, and sometimes you could make a much smaller circuit, in general, circuits and formulas are pretty big for pretty much anything. So you wouldn't be losing that much by going that route to encode a really complicated function, at least. So let's see how to do it. Suppose you have a Boolean function, and you know that if you set its first variable 1 and your second variable to 0 and your last variable to 0, it will evaluate to 1. Now it's not really a majority, it's just some function. So let's call its inputs A, B, and C. Well, we usually call things x, y, z, or x1, x2, x3, but for this one, let's say A, B, C. Now, how do we encode just the statement that the function on inputs 1, 0, 0 evaluates to 1? First, we can look at the question, is the first input 1? Yes, no. Is the second input 1? Is the third input 1? So we could set variable A corresponding to the first input to true, because the first input is 1, and B and C to false. So the formula which will encode that function should be true on its three propositional variables, when the first variable set to true, second one to false, and the third one to false. Now, let's write a formula that says exactly that. I'm true if the first variable is true, second variable is false, and the third variable is false. And we could write it by saying first variable is true, A. Second variable is false, that is, it's not that the second variable is true, and it's not that the third variable is true. And that's it. Here is a formula that codes up the fact that f evaluated to 1 when 1, 0, and 0 were its input. It doesn't say anything about f values on other inputs, or actually, in fact, if you only have this formula, then it will only be 1 for this particular input, but we will handle that in a moment. So suppose now that this function is 1 in 2 places and 0 everywhere else. You could write the fact that it's 1 on 1, 0, 0, as we just did, as A and not B and not C. And you could write the fact that it's 1 on 1, 0, 1 as A and not B and C. Finally, here is a formula that will be true if and only if the function is 1. It just says its input is either 1, 0, 0 or its input is 1, 0, 1. Since the way we define the function f was to say it's 1 in those 2 places and 0 everywhere else, this formula will be true exactly the same places when the function is 1. So we talked about product of sum formulas, which were of the form an and on the top, then there are ors, and each or only has either variable or negated variables underneath it. So for example, x or not y and not x or not z or w and x was an example of a CNF. If we look at the negation of a CNF, we will have a formula of the form an or, of an and also of variables and negated variables after we propagate all the negations to be on literals as we usually do. For example, if we negate this formula, x or not y and not x or not z or w and x, we will end up with not x and y, or x and z and not w, or not x. So we have a slightly different terminology when we talk about formulas of this form. An end of literals is called the term. And the whole formula is called the DNF, disjunctive normal form, where disjunctive is a fancy word for or, just like conjunctive was a fancy word for and. So why am I talking about it? Remember that we wrote down the full description of that function that was outputting 1 in 2 scenarios and 0 everywhere else as a OR of descriptions of the scenarios where it outputs 1. Or I should say as an OR of formulas that state that in those scenarios the function evaluates to 1. So the formula is true. So it is on the form of OR of ends of literals. It is in DNF, disjunctive normal form. This particular formula is called the canonical DNF of the function f. So the resulting formula encodes the value of the input value list of the function f, on which f outputs 1. And each of them it encodes as a term. So for example, the f that we just did on the previous slide was 1 in 2 places, one of them corresponding to a and not b and not c. So that is first input 1, second input 0, third input 0. And the second one, a and not b and c. So the first input 1, second 0, and the third 1. We call such a formula canonical DNF of a function f if it has a term for every possible list of input values on which f outputs 1. So if there are only 2 points, 2 possible scenarios where f outputs 1, as we just saw, then its canonical DNF would have 2 terms. If it outputs 1s everywhere, then it will have as many terms as there are lines in the truth table. Every Boolean function f has a canonical DNF, as you could see, because every time you start with a truth table, you could look at the lines that have 1, and for those lines, you could write your formula. What if there are no lines which are 1? Well, you could just write something that's always false. Okay, so let's try to do an example of constructing a canonical DNF. And for that, we will use the majority function, which, remember, outputs 1 when at least 2 of its 3 inputs are 1, and outputs 0 otherwise. So there are 4 possible scenarios out of 8 where majority will output 1. Scenario where all 3 of its inputs are 1, and 3 scenarios where 2 are 1 and 1 is a 0. So here's how we write those scenarios down. The one where all of them are 1, we write as x and y and z. And now I'm just abusing the notation by treating x and y and z as true falses rather than 0, 1, because I'm really thinking of a 0 as a false and 1 as a true. So x and y and z, thinking of conversion from 0, 1s to true falses, will be true only in the very first scenarios where x is a 1 or true, y is a 1, and z is a 1. Similarly, second scenario is x and y and not z. Third scenario is x and not y and z. Fourth scenario we don't need to encode because majority for the fourth scenario, for the fourth line of the truth table, is 0, because there is only one variable x out of the 3 that's 1 and the rest are zeros. But instead, the fifth line has a 1 in it for majority, so we need to encode it, not x and y and z. Now the canonical DNF for majority is just the OR of those 4 formulas. And notice again that this is a long formula. we were able to encode majority by a formula which in fact very DNF a lot shorter. That's true. Canonical DNF are not the most efficient way to code circuits, but at least there are a way. Once you have some formula, you could start optimizing it, you could start combining things, you could start making things smaller. But having a canonical DNF for every possible Boolean function you could think of allows you to say, no matter what I need to compute, if it's Boolean, I can compute it. I can make a formula, I can make a circuit. So similarly to canonical DNFs, we also have canonical CNFs. And probably the simplest way of thinking about canonical CNFs is just to think of them as negations of canonical DNFs for functions that compute the opposite. So it's kind of like a double negation idea, except it switches the form in the middle. So in order to make a canonical CNF, that is CNF that precisely encodes the truth table, we will take the function and make for which we need to write it, and write a function that does the exact opposite. Every time our function outputs 1, that function would output a 0. Every time we want to output a 0, in that scenario, that function will output a 1. Now, we could use the same idea that we just had to write a canonical DNF for that function that does the opposite. Finally, we take the negation of that DNF in order to go back to computing our function, the one that we started with. And remember, if you take a negation of a DNF, we get a CNF. And this will be a canonical CNF. The reason it's canonical is because just like canonical DNF have a term for every assignment, every scenario in which our function outputs a 1, a canonical DNF will have a clause for every assignment on which the function outputs a 0. So another way of saying it is, if you want to construct a canonical CNF directly without taking a negation on negation of a negation, you look at all the lines in the truth table in which your function outputs a 0, and then you write a formula that says, oh, this doesn't happen. So if you say that it does happen, as in it can be true that this scenario appears, you say the first variable and the second variable and the third variable, where you put negations where you want the things to be false. For example, if you have an assignment, first variable true, first variable false, second true, and the third false, you would write it as not A and B and not C. To say that it doesn't happen, you put the negation in front, you De Morgan it, and you end up with A or not B or C. Finally, your canonical CNF will just be an end of clauses like this. And the meaning of that is that first bad thing doesn't happen, second bad thing doesn't happen, and so on, none of the bad things happen. Okay, let's do an example. So suppose now for the formula, for the function that's majority, we want to write a canonical CNF. Let's now look at the negation of majority of the function that does the exact opposite. The function that outputs a 0 whenever majority would output a 1. It's very easy to convert the truth table for majority into the truth table for its opposite. Just switch all the zeros to ones and vice versa. So now if you pick the scenarios in which that second function is true, or the second function outputs a 1, those exactly scenarios where majority outputted a 0. And as before, we could write them down, and we could make them into a DNF for that function that does the opposite of majority. Finally, we take that function, we write several ugly looking lines doing our De Morgans and double negations and simplifying things. And at the end, we get a formula which is the end of ORs of literals and which has a clause for every single scenario, every single line of the truth table where our original function majority was outputting a 0. So you may be wondering, we were talking about CNFs in two very different ways. We were talking about CNFs when we were talking about resolution proofs by saying, let's convert our premises, let's convert our problem into some form which would make it easier for automated provers to deal with. And suddenly now we are also talking about CNFs, except we are calling them canonical. In fact, both are CNFs in a sense that both are ends of ORs of literals, but they play a very different role. For proofs, we start with a formula which we hope is not as big as a truth table. If it's as big as a truth table, really we might as well just write a truth table. We are not going to lose too much time doing it. We are thinking of starting with a pretty small CNF and trying to figure out whether it's a contradiction without going through all this work of writing out the gigantic truth table. On the other hand, when we are doing a canonical CNF, we already know what our function evaluates to, what our formula is on any given input. We absolutely know whether it's a contradiction is false everywhere, whether it's true everywhere, whether it's true in some places and false in others, and we know exactly where this happens. But what we want now is to go from a truth table to a formula, to actually write something that maybe we can then go and implement as a circuit that would compute the function. Again, our canonical CNFs are going to be as large as truth tables, but that's not a problem at this point. We are not really concerned with the size of the canonical CNF if we're starting with truth tables as our input. At the very least, we will have to spend all this time reading the truth table. So having a canonical CNF being big is really not such a big deal. Of course, in practice, you'll want to simplify things and so on. But again, here the role of a CNF is just going from list of values you want to get out of the function to something that can actually compute the function. Another thing is that the fact that we can write canonical CNFs and DNFs is useful for something else, for something more general about logic. What existence of canonical CNFs and DNFs for any Boolean function, for any truth table tells us is that everything, every truth table, every Boolean function we can think of can be written as a formula using only and, or, and not, which really supports that idea that we were talking about before, that implication and if and only if are just syntactic sugar. We don't need them. We could get away with just and, or, and not. Moreover, another cool thing that comes out of existence of canonical CNFs and DNFs is that you can actually prove that the two formulas are equivalent to each other using just the laws of logic, the logic equivalences that you've seen at the beginning. Okay, how does it even come in? Why is it relevant? Well, you could actually show that given the logic equivalences, you could convert every formula into its canonical CNF or canonical DNF. Now, here is a strategy for checking whether two things are equivalent. By using only the rules of logic without explicitly writing the truth table. Keep applying the rules of logical equivalences until you get a canonical CNF or a canonical DNF. Let's say canonical CNF. Do it on the first formula, do it in the second formula. If you got the same answer, they are equivalent. If you got a different answer, they are not equivalent. And that's as simple as that. So it shows that every time two things are equivalent, you could actually prove it.